In this video, I'm going to explain how to improve the basic common emitter amplifier. At the end of the previous video, I mentioned that there is something wrong with this biasing technique. So what's wrong with this technique? Let's now try to understand in more detail why this circuit is not very practical. We know that the quiescent base current IBQ is fixed and is set by the base resistor RB. As this circuit is going to function as an amplifier, we must ensure that the transistor Q1 is operating in the forward active region where the base emitter junction is forward biased and the base collector junction is reverse biased. In the forward active region, the base current IBQ is going to be amplified by the common emitter current gain beta, and the amplified collector current ICQ is going to flow into the collector terminal of Q1. So the quiescent collector current ICQ is given by the product of the amplification factor beta and the quiescent base current IBQ. After we have determined the quiescent collector current, we can find out the quiescent collector voltage, which is the voltage at this node or the collector node. This voltage is given by the difference between the power rail VCC and the voltage dropped across the collector resistance RC. The voltage dropped across the collector resistance RC is the product of the quiescent collector current and the collector resistance. If we substitute the expression for the quiescent base current into this equation and then we substitute this equation in this equation, we can derive the equation for the quiescent collector voltage as a function of beta. Let's number the equations 1, 2, and 3. We notice that equations 2 and 3 both have a beta term in the right hand side. That is, the collector current and the collector voltage are both affected by the common emitter current gain beta. This is not an ideal situation because if beta were to vary, then both the collector current and the collector voltage would also vary. When we designed this circuit in the previous video, we assumed that beta for the transistor BC547B is 300. So we designed this circuit for beta equals to 300. However, we know that beta can vary significantly from sample to sample. Let's now find out what happens to the quiescent collector current and the quiescent collector voltage when beta varies. Here is a table which shows how changing beta affects the DC steady state operating point of the common emitter amplifier circuit. We designed our circuit assuming that beta remains fixed at 300. For beta equals to 300, we get 15 microamps flowing into the base, 4.5 milliamps flowing into the collector, and an output voltage of 4.5 volts, which is half the supply voltage. So this is the ideal case, but now let's look at what happens if we change beta. We can observe that when we change beta, there is no change in the base current, and that is expected, right, because the base current is fixed. But the collector current and the collector voltage both change significantly as we vary beta. In the worst case, when beta equals to 600, the collector voltage or the steady state collector voltage changes by as much as 94% from the design target of 4.5 volt. This results in the base collector junction to be forward biased and the transistor is now operating in the saturation region. So it is not functioning as an amplifier. So this restricts the usefulness of the transistor biased this way, and therefore we must find a better biasing technique which is less dependent on the current gain or beta of the transistor. We can improve the performance of the simple common emitter amplifier significantly if we connect the base resistor to the collector node instead of the power supply voltage. So this is the improved common emitter circuit, and by using this circuit we will get a more stable DC steady state operating point. The improved performance is obtained by employing negative feedback, or more specifically shunt voltage negative feedback. That is, a current proportional to the output voltage is fed back to the input. Normally when we use this circuit as an amplifier, we would have two DC blocking capacitors at the input and the output. I have renamed the base resistor from RB to RF, F standing for feedback. The rule of thumb when choosing the value for RF, or the feedback resistance, is RF equals to beta times the load resistance or collector resistance RC, which is this resistance. Since we have used the same transistor, that is BC547B, let's for the moment assume that beta for this transistor is 300. We have designed the value of the load resistance to be 1 kilo ohm such that when a current of 4.5 milliamps flows through the resistor, we get a voltage drop of 4.5 volt at the collector node in the DC steady state, which is what we want, because the power rail is 9 volt, and having a voltage drop of 4.5 volt will ensure that we get equal swing at the output. So if we multiply the value of the load resistance RC, which is 1 kilo ohms, by the beta of the transistor, which is 300, then we get a value of around 300 kilo ohms for the feedback resistance RF. We have chosen 270 kilo ohms because this is more close to a standard resistor value. Before I go into detailed DC analysis of this circuit, let me first explain briefly how this circuit achieves a more stable bias point. So we have a current flowing through the load resistor RC. This current is equivalent to the emitter current. That is, this current is the same as the emitter current, which is flowing into ground from the emitter. Now, because of the shunt resistance here, the emitter current is split into the collector current and the base current. As a result of the base current flowing through the shunt resistance or feedback resistance RF, we get a voltage drop across this resistor. Let me get rid of some of the clutter so I can explain things more clearly. Let's label the terminals of the BJT: base, collector, and emitter. Now, if we apply KVL across this network, we can write VC, or the collector voltage, equals to IB times RF plus the voltage across the base emitter junction. From this equation, we can obtain an expression for the base current, which is IB equals to VC, or the collector voltage, minus VBE divided by the feedback resistance, RF. Now let's say that we use a transistor which has a beta much larger than 300. Larger value of beta would result in a greater emitter current. We can write IC, or the collector current, equals to alpha IE, where alpha equals to beta over beta plus 1. As alpha is very close to 1, the collector current is also very close to the emitter current. So if the emitter current increases when beta increases, the collector current will also increase. A larger collector current would result in a greater voltage drop across the collector resistor. The collector voltage would fall, and from this expression we can see that if the collector voltage falls, we will get a smaller base current. So the net result is higher gain offset, in part by the smaller base current, so that the collector current rises less. We call this negative feedback because the increase in collector current is counteracted. In this situation, the negative feedback leads to reduced amplification, but with correspondingly less distortion at the output. More importantly, we can use absolutely any NPN transistor in our junk box to build this circuit, and it will work each and every time. Or expressed scientifically, the circuit can tolerate a wide variation of samples. Let's do a more detailed DC analysis on the improved common emitter circuit. So we want to find the operating point. More specifically, we want to find the quiescent base current, the quiescent collector current, and the quiescent collector voltage. We want to design the circuit such that the quiescent collector voltage, or the output voltage of the circuit in the steady state, is half the supply voltage, or 4.5 volt. So we want VCQ equals to VCC over 2. Now the first parameter of the operating point that we need to find is the quiescent base current. The base current flows through the shunt resistor RF into the base terminal of the transistor Q1. Let's label the transistor terminals again: base, collector, emitter, and this voltage here is VBE. We know that the base emitter junction voltage, VBE on, is equals to 600 millivolts. Taking the KVL across this network, we can write IBQ equals to VCQ minus the base emitter junction voltage divided by RF. This gives us VCQ is VCC over 2, so that is 4.5 volt, minus VB is 600 millivolts divided by RF, which is 270 kilo ohms. So this gives us a value of IBQ of approximately 15 microamps. Now, assuming that the transistor is operating in the forward active region, we can write ICQ equals to beta times IBQ. This gives us a value of 4.5 milliamps. To calculate the value of the quiescent collector current, we assume that beta is 300. We know that the quiescent emitter current, IEQ, is equals to the quiescent collector current divided by alpha, where alpha is very close to 1. It's something like 0.997. So the quiescent emitter current will be only slightly larger than the quiescent collector current. So a current roughly equal to the quiescent collector current would flow through the collector resistance. As this current is very close to 4.5 milliamp, and 4.5 milliamp flowing through a 1 kilo ohm load resistance would result in a voltage drop of 4.5 volt. So the voltage at the collector node would be 4.5 volt, which is exactly what we want. So this would result in VCQ equal to 4.5 volt. By calculating the values of the quiescent base current, the quiescent collector current, and the quiescent collector voltage, we have determined the operating point of the circuit. Let's now find out how stable this operating point is if beta of the transistor varies. This is the table of different operating points for the common emitter circuit with shunt voltage feedback as I varied the beta of the transistor. This is our target operating point where we design the circuit assuming that beta is equivalent to 300. The first thing we notice is that when we change beta from 300, the quiescent base current changes, unlike the simple common emitter circuit where the quiescent base current is fixed. Although the quiescent collector currents and the quiescent collector voltages vary as we vary beta of the transistor, this variation is not as large as that observed in the simple common emitter circuit. And in the worst case scenario where beta takes the value of 600, the quiescent output voltage or the quiescent collector voltage has only changed by 29% compared to 94% for the simple common emitter amplifier. This means that with the common emitter amplifier with shunt voltage feedback, when beta equals 600 in the worst case, the output voltage having a value of 3.2 means that the base collector junction is still reverse biased, and therefore the transistor is still operating in the forward active region. and functioning as an amplifier. So this table of data proves that the common emitter amplifier with shunt voltage feedback or negative feedback has a much more stable DC operating point. Before I finish, I want to discuss one last thing. Let's analyze this circuit slightly differently. If we apply KVL across this network, we can write VCC equals to IE RC plus IB RF plus VBE. Let me show the collector current in the circuit diagram. Now we can express IE, the emitter current, as the sum of the collector current and the base current. Which is equals to beta IB plus IB. This can be expressed as IB beta plus 1. Therefore, IB, or the base current, can be expressed as IE divided by beta plus 1. So we can substitute the expression for the base current into this equation. Let me get rid of some of the clutter. So we know that IB can be expressed as IE by beta plus 1. So substituting the base current into this equation, we get VCC equals to IE RC plus IE beta plus 1 RF plus VBE. So now we can express this equation in terms of IE, that is the emitter current. So if we do that, we get IE equals to VCC minus VBE divided by RC plus RF by beta plus 1. Now if we look at the denominator, we notice that if we engineer or design the feedback resistance such that this term is smaller than this term, then the emitter current would be less dependent on beta. So if RC is greater than RF by beta plus 1, then IE would be less sensitive to variation of beta. Since the collector current is very close to the emitter current, if we design this circuit such that the emitter current is insensitive to beta variation, then the collector current would also be less affected by beta, and therefore we would achieve a much more stable DC operating point. This concludes the DC analysis of a common emitter amplifier employing negative feedback. In the next video, I will present the DC analysis of an even better common emitter circuit. Thanks for watching.